Okay. I was just checking that I put everything on that is on YouTube on the Canvas website, and I was curious to see how many followers I have. 980. So I'm 20 followers short from what? Starting to earn money? I don't know if this is even real, is it? Like they would start putting advertisement on my videos or something? Really?
You'll get like a couple cents.
No, but I don't want advertisement when people are watching the lecture. Oh, we can? Okay, good. I'll ask you another time. Couple of cents, huh? Have you tried it?
I think it's like 1 cent for like 10,000, something like that.
1 cent for 10,000 reviews?
It's like
It's a ripoff, basically.
you have to have it.
Okay. All right. Okay, so let's pick up where we left off. All right. Just a couple of recap questions. We were talking about different methods of separation. What are some chromatographic methods of separation that you can remember? Target fusion, very common in the protein world. What else? Ion exchange, mostly anion exchange. What else? One we use in our lab quite a bit. That's not here. Huh? Well, it is HPLC for protein, so they're not volatile, so you cannot use VC. But no, it's the mode of separation. Mode of separation would be by size inclusion, by charge, anion exchange, and by hydrophobicity, hydrophobic interaction. These are the main ones, but also so there is a chemical component that is usually used to purify enzymes or enzyme inhibitors or antibodies. Okay. So proteins can be separated based on differences in solubility. So what are some examples of protein separation that is based on solubility? Oh, Dressa came. There you are. Yeah.
Salt, so like salting in protein, like ones that are salt concentration.
So salting in, and sometimes we add a little bit more concentration to salt out. So use of salt, basically. What else? Very common as well. You change what? To make the proteins more soluble or less soluble? pH, yes. So you choose the pH at which protein is most soluble, and then if you want to separate it from other components that are soluble, that means. Did you hear that or just I heard that? No, I don't know what that was. We do isoelectric precipitation to separate protein from other solubles. So pH, so salt, pH, what else you can do? What happens if you heat and denature the protein? They can aggregate. Yeah, they can aggregate and fall out of solution. So you lose solubility. You can separate them that way. But usually for protein and lignin, we don't go that route because you want to maintain the functionality of the protein. Organic solvents was another one. You can precipitate proteins in the presence of photographs. Okay, very good. What else do we have? Structural characterization. What do you remember of some assays that are very common for structural characterization? Oh gosh, I walked in without my demos. Anyway, yep. What's that? Yeah. Circular dichroism, we do, it's mostly instrument based because you're looking at the standard structure of protein, let's say, using the instrument. But if you're thinking of a chemical act, what would be a chemical assay used to look at structural characteristics? Surface, yes. Surface hydrophobicity is a very common method to determine whether or not the protein is natured or how more hydrophobic this protein is on the surface than another protein. Look at the impact of processing on the surface properties. So that another example we'll be looking at, but it's instrument. Yeah. Huh? Zeta potential? Yes. Yeah, I know I put it under chemical because you can measure it using chemical titration or you can measure it using our zeta sizer. Okay. Another one that is used a lot in the lab is amine blockage. We looking at primary amines. What time we can look at it for determining if amine got taken up in chemical reaction, like Maillard reaction or transglutaminase reaction where glycine is linked to glutamine. Or sometimes to measure degree of hydrolysis, we determine how many more free amine is there to react with OPA agent. Okay, so these are some examples where others like total sulfider groups, surface sulfider groups, all of that. Any questions about the material we learned so far? Anything you're curious about? I didn't explain very well, or I went so fast on it. You know, questions are welcome. Don't be shy. If you already started studying, everybody will learn from your question. And no question is not a smart question. All questions are good.
I have a question.
Yes.
In last class, you mentioned that you don't prefer to do total sulfide review or thin sulfide review.
We don't prefer?
Yeah, something you mentioned that. It's like it's usually not used, but
We in the lab we don't use it. Yeah, but it is used. Yeah.
that's why I was really.
Yeah.
I did.
Yeah.
Do you have any-
It's valid, I say it's a little bit more, involved. You're measuring it just to determine the protein nature, there are other ways to determine. If you're measuring it to see how much disulfide interactions you actually form under certain conditions, it's a very valid assay. Yeah. Oh, that's good. Yes.
So I was wondering if disulfide bond is considered a post-translational modification.
It can be, it is, because sometimes proteins are stabilized naturally by disulfide interactions. And it is, when you form the protein, like I said, when it's just an amino acid sequence, it has a lot of free energy. So bonds start occurring to reach to a most stable state. And if the protein has a lot of sulfider groups, as the protein is folding, as happens to contain the free energy. So it can happen at the cell level, but also, for example, beta-lactoglobulin, whey protein, it has 5 sulfider groups. 4 of them are already SS in the native, and 1 free sulfider group. So that's in the native form of the algae. But when you process, it's in the inside of the molecule. When you process, you denature it, and then you have SH group available and another molecule SH, then you form SS linkages. Also in gluten forming proteins, glutamins and gliadins. When you're kneading and denaturing, you open up and you expose the sulfide gluten and disulfide interaction happens. So to answer your question, it can be both in cell formation of the protein and also gluten process. Okay, very good. Other questions? All right. So to continue, from where we left off, we started talking about instrument-based. We talked about DSC, mostly used for denaturation, identification of denaturation temperature, and entropy of denaturation. Sometimes if the protein is completely denatured, we don't see any of the variants. We talked about that. We talked about protein secondary structure, which can be done by FTIR, but also circular diaphorism is another way of determining protein secondary structures, protein tertiary structure, by Raman, we talked about that, and also actually NMR. You can do NMR to determine protein structure. And then we have aggregation. We do, like I said, electrophoresis. I will explain. Oh, that's another technical method. Is looking at molecular weight distribution and polymerization using electrophoresis. Mostly we do STS phase, sometimes we do urea phase, to remember for proteins specifically. But another form or method, which is instrument-based to determine protein aggregation, we do it a lot in our lab, is looking at molecular weight distribution using size exclusion chromatography. So we usually run the protein along some controls and references. If we have the most native form of the protein, we run that, and then do the processing, whether hydrolysis or polymerization, due to heating, we can look at the distribution of the molecular weight using size exclusion. Now, we usually link it in the lab with PDA for the diode detector, so based on protein absorption of light. But the best way, most precise, is having a detector known as multi-angle laser or light scattering. NONS. Stupid expensive. We're talking hundreds of thousands of dollars. So I don't have it, and I typically manage to buy it. So one day, maybe we'll get it. It gives you really accurate more accurate molecular weight distribution. Because it's expensive, most labs don't have it. Based on size, actually, sometimes movement in the column is also based on the diameter of the protein.
So it shows if the degradation happened.
Yeah, I'll give you an example.
So it shows.
It shows aggregation. Sometimes it's not really a quantitative measure of aggregation. It just shows you the relative distribution. Aggregate, what is it?
Denaturation, degradation. Meaning that
we don't see denaturation, just like going from native states to native states is not a method for that. But it also shows you if the protein is hydrolyzed, it will show the human degradation. Yeah, it shows the breakdown of protein. And I'll give you an example on that. Aggregation can also be visualized by looking at the larger visualization of the morphology of aggregation. We use SEM to look at that. And this is an example where we use size exclusion actually for hydrolysis. So here in this example, we had whey protein and we subjected it to enzymatic hydrolysis using trypsin, which is an endoprotease, and another enzyme that is mostly exoprotease. So what we did is we looked at alpha-lactalbumin and beta-lactoglobulin. So this is beta-lactoglobulin, this is alpha-lactalbumin. And we looked at the formation of hydrolysates under different conditions by different enzymes. And we collected the peptide fractions to characterize those peptides and determine selectivity of the enzyme and also characteristics of the peptides. So as a first step, if we want to identify the protease specificity, and then we need to identify characteristics on the peptide. First of all, we need to, separate them and then collect their peptides. So the easiest way of separation was the size exclusion, and it gave us quite a bit of information. So beta-lactoglobulin at pH 7 is in the dimer form. So when we run the size exclusion chromatography on beta-lactoglobulin, we see it as dimer. So the molecular weight of that is really not 18, but 36 is the molecular weight. And then we hydrolyzed with trypsin. We saw that trypsin mainly is specific to hydrolyzing beta-lactoglobulin with not much of alpha-lactalbumin impacted. But when we did protease, and one type of aggregoprotease, at the degree of hydrolysis of 8% and 12%, we see that it does. Somebody's trying to text me on the a Google chat. We see a change in the relative abundance of beta-lactoglobulin and also the relative abundance of alpha-lactalbumin. So both proteins were hydrolyzed by that exopeptidase to a different extent based on the degree of hydrolysis. So that was very informative using just size exclusion. Another example where size exclusion was used is by looking at polymer formation and soluble aggregates formation. So this is a pea protein. We looked at soluble aggregates, which are mostly around the 1200 kilodaltons. And then legumin is in its hexameric form, convicillin in trimeric form, and vicillin in trimeric form. When you run on HPLC and HPLC, you have to filter. You cannot run the protein directly on the column because it will follow the column. So a lot of aggregates don't really make it on the column. So what we see are soluble aggregates that goes through the filter and non-aggregated proteins. So if we look at the commercial pea protein, we hardly see any functional proteins. It's mostly a little bit of soluble aggregate, but a lot that was filtered out because of the large aggregates in this commercial sample. Then we have the sample that we produce in the lab, and then all of these different samples are treated by plasma species. And then we can see that with specific plasma treatment, we get more soluble aggregates compared to the control. So cold plasma resulted in the formation of soluble aggregates that enhance the gelation properties of. So when we do structural characterization, we do it so that we understand any functional change. So why something changed? Why did we have better gelation? So we looked at a molecular structure to kind of link structure to function. And that was one incident as well. Questions? Do you in your research need such characterization? Anybody? Well, our lab obviously does that a lot. Do you? Do you have an HPLC in the lab? You can ask us for method if you ever want. No? Why are you not happy?
It's really challenging.
What is?
It's really challenging.
Come to us, we'll bring. Right, where's Mateus? He ran away. Mateus, you have a job.
I'm here.
Okay, so no, seriously, if you need support, listen. It's not as hard if you have a system that works.
No, it's not hard, but every time I see a new peak, the shape of the peak, the retention time, everything, the very small changes make a big reaction in the.
You know what I can offer you is look at your chromatograms and try to help you navigate why the change, whether it's method related or sample related. All right, so next one we've used quite a bit is we use mass spectrometry. So we call this the use of protein and mass spec proteomics. So we use it in so many different ways. I will just give you a few examples on that. MALDI-TOF, who knows what it stands for without looking at him? Okay. Matrix. Yeah, laser desorption. Ionization. Yes, because you have to ionize in mass spec. All right, and what is top? Time of flight, not a toffee or anything. Okay, so time of flight. Yes, we use it quite a bit, and I'll give you an example. If you have small molecular weight proteins like whey protein that are not aggregated, it's perfect to run directly on MALDI. You don't have a chromatographic separation with MALDI, so direct you put the sample on a plate and you have the matrix and then laser directed to it. So no chromatographic separation needed. So if you have a very pure protein, you can, and small molecular weight protein, you can actually make it fly. I'll talk about flying in a minute. And then you can measure the accurate molecular weight of that protein. So it's a very useful technique if you have very pure protein and also relatively small molecular weight. If you have proteins over 50 kilodalton, it will be hard to make them fly. If you put analysis in Gary Pot, he always gives the example, can you make an elephant fly? Well, in his opinion, you can't make an elephant fly using this technique. But let's start, I want to remind you that every on Canvas, every week, if there is additional reading, I put it in that week. So I have a summary of all of these methods on Canvas. So this is FYI, if you want to learn more about MALDI and how it works, there is a brief document that talks about it. But in very high level, so you would put your sample with a matrix. And usually your matrix is a weak organic acid that is very ionizable. So when you put your protein sample, pure protein sample, with this organic acid, and then laser is focused onto that sample in a matrix, it gives a lot, the organic acid absorbs all this energy that is coming from the laser and ionizes your protein and makes it fly. Gives it a lot of energy to fly into a tube that goes to a detector to determine the molecular weight. And then the smaller the molecular weight, the faster it's going to move. And the smallest reach the detector first. Okay, the larger it is, the slower it is. That's why it's called time of flight. So the time it takes to reach the detector. And that's why large proteins won't fly either. So it will be very hard to actually get a signal when you have large molecular weight proteins. So it's very good for small molecular weights, proteins or peptides. Oftentimes, if we have a very pure protein, you can actually do trypsin hydrolysis. So you break it, because trypsin hydrolysis, trypsin is very specific, so there are databases for the peptide generated using trypsin on particular proteins of interest that we are studying. So sometimes the protein is hydrolyzed by trypsin, and then the peptides are run through to determine the characteristics of the peptide. So I'll give you examples. So yeah, so that is just telling you, take a protein. The reason I have this gel here, it's a 2D gel. So what I'm trying to illustrate here, if the more pure your protein fraction, the better. Then you won't have, false information from different proteins. So oftentimes we run size exclusion and then we separate by the gel or do 2D gel to get as much of a pure sample as possible. And then you run it through hydrolysis with trypsin, and then you run it on your mass spec time of flight, and then you get a spectrum. What is it used for? If you have a peptide that you're trying to characterize, it can give you the sequence of the peptide by breaking one amino acid at a time, not necessarily in this case by trypsin, by another exopeptidase. And then what you see are peptides that are smaller by one amino acid that you can determine what they are. From one, let's say 1,229 to 1,344, the difference is aspartic acid. And the next peptide, the difference is glutamic acid. And then serine, alanine, etc. So you would determine not only the molecular weight, but the sequence in this case. You call that ladder sequencing. Another example, we've used it in the past. We were glycating whey protein. That means we are taking whey protein and using the Maillard reaction to attach a maltodextrin and enhance solubility. We wanted to observe or explain some observation. The protein, when it was glycated, it resisted unfolding. So we wanted to understand why it resisted unfolding. So which lysine got linked? So what we did is we took out glycated protein. First of all, we hydrolyzed the maltodextrin because you have maltodextrin attached. So we wanted to break off the maltodextrin so that you only have one glucose or two glucose attached to your protein so that it can fluid out. And then we did trypsin hydrolysis and we identified this peptide, and there is a lysine in this peptide based on the increase in molecular weight that matches one glucose member. So we were able to determine which lysine was linked to your sugar using MALDI. And the location was very critical in us understanding why the protein resisted unfolding. So yeah, so it was very cool observation. LC-MS also has its own advantages and uses. We use it to identify proteins that come up from different genetic variants, for example. If you have, like, in Nigel's case, one of my students, he's looking at 200 different oat varieties, and he's looking at the differences in the protein distribution across these varieties. So we do LC-MS to determine those varietal differences or genetic variants. Sometimes we use it to determine the identity of the peptides generated by hydrolysis. So identification of source of protein, that is one application. Another application, if you hydrolyze, it will give you some information about the peptides generated. I'll give you two examples how it was used. So in this research, we were looking at the time many years ago, we were looking at generating peptides or hydrolysis from soy protein that have antihypertensive activity. And we used to do the testing using an in vitro assay and calculate IC50. Who's familiar with this term? Have you encountered this term before? IC50. You encountered it, you remember what it is? Huh?
Like some,
It's after that, accident, factor of the antioxidant test,
What?
antioxidant.
Antioxidant, you can use it for antioxidant, you can use it for antihypertensive purposes. Safety benefit? Okay, so you've seen it, but what does it mean? It has to do with an amount. Anybody? Okay. So the assay in that we measure a degree of antihypertensive activity. It's an inhibition. So inhibition of a particular enzyme that is responsible for increasing the blood pressure. So I stands for inhibition and C stands for concentration. And 50 is the concentration that causes 50% inhibition. That's what it is. Now, the inhibition can be of anything, but in this particular case, we were looking at the inhibition of a particular enzyme, and we tested that in vitro. So, just to understand the example, I needed to explain IC50 is, and the smaller number is the more potent. Why? Because at lower concentration, you get 50%. Okay, so the lower the number, the higher the potency of the inhibition. Okay. So that's to understand what IC50 and the example. Okay. So, you know, I like telling stories, right? So what I wanted to explain so that you understand the story. So here the objective was, you know, 12 years ago or even more, there was this notion of producing those pharmaceuticals that are potent, like take a pill of a hydrolysis, a purified hydrolysis as preventative medicine. So it takes a lot to take a soy protein and fractionate and get one particular protein and hydrolyze it to get one particular that has good activity. So what I was trying to prove in this study is that if I use a particular enzyme that is very specific, I can get to the same outcome without having to fractionate. So meaning I get soy protein, I hydrolyze soy protein, and I get the same outcome from hydrolyzing a purified protein. Okay, so I was very optimistic and saying we don't need to fractionate. We can get the same outcome in a mixture. And that's what I was looking. So soy protein isolate, comparing it to a purified component of the protein, which is beta-conglycinin, and this is glycine. One article showed that beta-conglycinin peptides are more potent than glycinin peptides. Okay. So they purify beta-conglycinin and they hydrolyze beta-conglycinin to get the potency. So what I said here is like, okay, we can get the specific enzyme that hydrolyzes beta-conglycinin, but instead of purifying and hydrolyzing the pure form, let's just use that specific enzyme directly and see if we get similar results. And we did. We got similar inhibition. So similar potency. And the degree of hydrolysis was more in the purified form. But anyway, if I want to compare enzyme that hydrolyze specifically glycinin and enzyme that hydrolyze specifically beta-conglycinin, I proved that beta-conglycinin hydrolyzes more potent than glycinin hydrolyze, but I really don't need fractionation. I can use a specific enzyme and get the same outcome. Okay, how did I fix that? not only by experimental, I mean, okay, yes, papain was specific. So here, let's see. Okay, so this F here is soy protein with papain. So I targeted beta-conglycine. You don't see bands here. So it was a very targeted enzymatic action. Very good. I got targeted enzymatic reaction. I got good inhibition, similar inhibition, and I used LC-MS-MS. What am I looking at here? Is we took the peptides of SPI hydrolyzed directly, and also in this case, glycine in this example, the pepsin hydrolyzed glycine, and we found all these peptides in both the hydrolyzed SPI and the hydrolyzed glycine. So basically, we've proven that we don't need fractioning. We can get the same outcome. So that was how we use LCM. Is it too confusing? Right, were you following? Yeah, okay, good. Another example where LC-MS-MS was very, very helpful is, remember that size exclusion figure that I showed you with whey protein and hydrolyzing it with trypsin and hydrolyzing it with protease M. So we took those peptide fractions and we analyzed them by LC-MS-MS, and we were able to determine the peptides generated and where the enzyme cut based on the enzyme that is used, and the protein in this case was beta-lactam. And what we did with this information, we mapped the peptides, and we were able to map something called Gravy score. Gravy score allows us to determine the relative between hydrophobic and hydrophilic properties. So with trypsin, so positive Gravy score is for hydrophobic, negative is for hydrophilic. I'm not going to go into detail of why and how, but with higher degree of hydrolysis, we get more hydrophilicity from the trypsin hydrolyzed. But usually trypsin gives you a good balance of hydrophobic and hydrophilic, and we saw an enhancement in emulsification properties. So it explains to us that with using trypsin, you get better balance between hydrophobic and hydrophilic. That's why we see enhancement in emulsion. Whereas when we did the protease M, we saw more hydrophilicity, especially as your degree of hydrolysis increases with smaller peptides. They're very hydrophilic, and this fraction is very soluble. So this explains higher solubility. So we were able to use structural information to explain algorithm. NMR, analytical, I won't use it, but you can use NMR to determine structural configuration by monitoring the proton spectra. Basically, how close protons are to each other. It will give you solve the puzzle and gives you the final structure of the protein based on the proximity of hydrogen. So it is used, it can be used. I don't have examples for you, so I didn't use it. But if you need to know more about NMR, again, there is a document that summarizes how NMR used for protein determination. Okay, moving on. Any questions so far? All right. Amino acid analysis is commonly used as form of structural characterization. Why? What does amino acid analysis, compositional analysis tell us? Why do we use it? Use it in our lab, for example. Why do we use it? Huh? Limited analysis. Yeah, so we're doing amino acid composition to determine the nutritional quality of the protein based on the amino acids that are there. the essential amino acid. So that's one thing. What else? Do we use amino acid composition?
How much hydrophobic?
Yes, so we actually, I was gonna show an example. When we know the composition, we can determine how much acidic amino acid you have. Basic, hydrophobic, sulfhydryl group, cysteine, it's important. Okay, so yes, what, so understanding a little bit how the composition will impact functionality. One more. Identifying a protein, a new protein. Whenever you discover a new protein, the first thing you want to do, let me look at its amino acid composition. Yeah. And if you know the amino acid composition, you can actually determine how much amino acid you have. And then you will be able to add all the molecular weights of the individual amino acid and get molecular weight of the protein. That's another way of determining molecular weight of the protein. How do we do it? We hydrolyze all the peptide bonds, break them into individual amino acid, usually strong acid with heat, certain time to get all of the amino acids. And then we separate. Mostly in our lab, we use reverse phase. We do derivatize so that we can measure absorptions. So all of them get derivatized by a specific reagent in order to determine the composition. And we talked about phthaldehyde can not only used for amino acid because it reacts with primary amine, it can be also used to determine degree of hydrolysis. But just to be complete, not all amino acids can be determined by just doing acid because there's degradation. So we lose tryptophan. That's why we need to do alkaline hydrolysis to determine tryptophan. We also need to do another step to determine cysteine methionine because they get oxidized during acid hydrolysis. And like you said, we determine the composition of key amino acids, like how much acidic, basic, ratio of acidic to basic, that will be an indication of net charge. Sulfhydryl groups, sulfur-containing amino acid. In this example here, this is hemp protein isolate, different varieties of hemp protein isolate. And you can see that the hydrophobicity is really, which is very common for plant proteins. They have really above 30, most of are hydrophobic. That's why we have a lot of surface hydrophobicity, because no matter how the protein folds, you can't hide 30% of amino acid inside of the structure. And that's why they form quaternary structures, because they want to hide from water, so they start forming those associations. Another structural testing is the sequence of amino acid. So the sequence is determined. Sometimes it's easier to determine the sequence by DNA and acid, the genetic coding. You can determine the protein composition sequence. But also another method is if you have a very pure protein, and we're talking above 99% pure protein, you can do this Edman sequencing. We call it N-terminal sequencing. Edman is the person that developed the method. And the reagent is called Edman reagent, but really what this reagent does is reacts with the N-terminal amine, breaks the first amino acid off, and goes into a sequence of reactions, and you get compound, yet you measure the absorption of. And this cycle repeats. So it goes one cycle, get an amino acid, goes into your chromatograph and get ionized, get detected, because you're on standard, so you get detect the identity and quantity. Then the cycle repeats, and then you get all of this amino acid by measuring by on a HPLC coupled with. It has to be pure protein. Oftentimes, you have to transfer. I got all the system and what is in the office. So you run SDS page, oftentimes 2D gel, and then you transfer all the proteins into a PVDF membrane, and you cut the band that is very, very pure at this point. And then you do this first cycle of analysis and the next cycle and the next cycle to get the sequence. ELISA. What does ELISA stand? What does ELISA stand for? Enzyme linked immunosorbent assay. So often, and Western blot, we got all the quick invested in the office. So, and ELISA is mostly used not just to determine immunoreactivity, but to identify protein in the food form. So if you want to identify the presence of a particular protein, you can use specific antibodies and use ELISA to determine the presence of, and sometimes the quantity of a specific protein. It's commonly used to, let's say, detect the presence of a different source of protein. Have you heard of the force contaminated food bag 2 years ago? No. 10 years ago now. And the way to determine whether this is completely unique or it has something else in it, you can use antibodies specific to if you're suspecting horse or suspecting other type of animal. And then you can determine whether you have that type of animal meat in the cattle. Huh?
They want to check if problem is present now.
Yeah, yes, exactly. So it's presence, identification of the presence of the suspect. Oftentimes also it's used to determine genetic modification. Here in all states university. Yeah, so allergenicity or GMO or contamination of other pathogens. I'm not gonna go into the how we run the ELISA, but I'm just telling you what it's used. Western blot, I was gonna show you it, and then I didn't get it, but Western blot is a form of course, it's an immunoassay, but it's qualitative, visual. So before you, if you have so many samples that you want to screen, instead of running ELISA assay, the 9612 with all the reagents and the washing that you have to do, you screen first and then limit the number of samples that you want to analyze, somewhat quantitatively or quantitatively by ELISA. Again, what you do is you would always have to be gel because you run your sample in 2-dimension to purify as much as you can. And then because the gel, of course, it's such easy to break, you cannot incubate it with the different reagent. You transfer, same thing. So you transfer into a PVDF membrane that is more sturdy. So you run, there is a special transfer compartment where you put the gel and the membrane, put them in a sandwich form, run it like you would run an electric gel, and the protein moves in one direction from the gel to the membrane. And you take that membrane and then you incubate it with the different reagents to induce the immuno interaction. And you put your enzyme labeled antibody, and then you put the substrate, you get the color, and you basically will see if you have your protein. So qualitative. This is an example where we used Western blot for modifying soy protein and determine if we reduce immunogenicity or immunoactivity without having to run all the samples on all the conditions that we test using the ELISA. So in this case, we ran the proteins. We looked on the gel and then we transferred. We looked at them, all these proteins that lit up, meaning all of them are allergenic. And then we subjected them to different hydrolysis, and with more hydrolysis, we reduced the immunoreactivity. And then we did Maillard induced glycation, different conditions, and we found a condition that was least reactive. The proteins in it was least reactive compared to the original protein. So we moved forward with that and did ELISA and did more testing. So this is just to illustrate Western blot. It's the screen. Screen the conditions of modification and determine which condition leads to less immunoreactivity in this case. Here is an example that I want to say sometimes you have to do multiple things to separate and purify the protein before you do your proteomics, for example. So oftentimes you have to do 2D, 3D chromatography in a row. So first dimension, second dimension, third dimension. In this case, this is an example where we wanted to isolate a peptide that has high antioxidant activity. This is not my work, so I'm just giving you an example. So here we hydrolyze, then we do ultrafiltration. What is the purpose of ultrafiltration here in this example? If I hydrolyze, say whey protein. Why is my first step ultrafiltration, and what do I want out of that? What's that? No, don't worry about salt and sugar. You have whey protein isolate, you hydrolyzed it, and then you did all
separate the undenatured from the nature. Or
which you mean the hydrolyzed, the small peptides
yes,
from the
small
body.
from the nature.
Because antioxidant peptides are usually small. So you can do 3 kilodalton or even 1 kilodalton. You can get rid of all the large peptides and non-hydrolyzed proteins. You don't want it. So that's the first step. So you do ultrafiltration, you get the permeate that goes through, and then now you want to purify. So we do liquid chromatography. You can do size exclusion first or ion exchange first. It doesn't matter. You can do ion exchange, then size exclusion, or the opposite. So if you do, let's say, ion exchange first. So you separate and then you take each fraction and you do antioxidant activity. It seems like the F fraction here has the highest antioxidant activity. But this fraction might have similar charge, but different peptides with different molecular weight. So you take that fraction that is not pure, then you run it on size exclusion. And you take each fraction and you get the antioxidant activity. Then you purify this fraction that might have similar peptides with similar molecular weight and similar charge, but they're not the same. So you run it another form of HPLC. You can run it on reverse phase and also take fractions and determine antioxidant activity. And then you take that one fraction running on MALDI, for example, and determine its molecular weight and do N-terminal sequencing or ladder sequencing by MALDI and identify. So oftentimes to reach your goal, you have to do many steps. This work What we are trying to do with this work is, when you work with the breeders, the breeder says, oh, I have 1,000 lines. Can you analyze and tell me which one is better than the other? Like 1,000 lines. Imagine how long it would take us to produce protein isolates from 1,000 lines. And to determine the composition and the ratio of different protein fractions forever. Now, we cannot keep up with breeding. Then we say, okay, maybe we can devise a rapid scanning method by FTIR. Okay, FTIR can give us unique molecular structure, but I need to calibrate. How do I calibrate an FTIR? With pure standards. So now I have to produce pure standards, protein fractions from P. Protein, so we can calibrate an FTIR and we can screen thousands of lines for their ratio of different protein fractions. The main fractions are legumin and viscerin. So in this case, what we did is a whole process of getting a legumin-rich fraction and a viscerin-rich fraction by liquid isolation, salt-based isolation. Then we run anion exchange and size exclusion chromatography to get a legumin fraction and a viscerin fraction. And here's your guy. Mateus, did you see yourself? He left. He just left. He left. Too bad. Anyway, so what we did after we purified by salt extraction, then we ran with two-dimensional HPLC, took the fraction, we sent it to LC-MS proteomics, and we confirmed that the 7S purified does not have any legumin in it. So we achieved a pure standard. And now this guy is working on purifying legumin so that we can confirm that there's no viscerin in legumin. Then we will have our pure standard that we'll use to feed the FTIR and calibrate so that we can screen hundreds of lines. All right. Too bad Mateus did not see himself featured. Oh, he's up there too. I don't know what he's doing up there. Okay. Oh, I thought I was done. No, this is also cool. Wait a second. This is another cool use of proteomics in a different way, where you don't actually do mass spec. You look at data sets that are available to us for free on compositional analysis and sequence of proteins that were characterized and the data published online. So this is work we did with hemp protein, different varieties, extracted different conditions, and we did amino acid composition, and we compared it to the amino acid composition of known components. Edestin is the main 11S globulin in hemp. And we looked at comparing the profile to what has been identified in literature to determine do we have which genetic variant is more dominant in these different varieties. So that was cool, theoretical comparison. And we used the theoretical data to compare Edestin to glycinin, which is 11S in soy, to see how close the structure of the different edestins from hemp compared to glycinin 11S. So that was cool, helped us in explaining the data and the observation and functionality. Go read the paper if you're interested. Okay, well, that was it for protein analysis. Do you have any questions? Do you have an example research you're working on that you can use any of these tools that you didn't know about and it will help with research? We can use the just like a few minutes break between going to the next subject. From what you learned, how can you apply it to research? Can anybody give me an example?
Now I work on figure out penetration on top like protein.
Mm.
And now I use the HPLC and precipitation in the isolated component that I can make in the liquid. But I need I think the better option for me is the side diffusion to see that how much degradate during the heating that I use the high heating in the low temperature in the short time. So I'm sure that I have a degradation. But I don't know the more option and useful or not, but the side diffusion is in my plan.
Yeah, very good, thank you. What else? Yes,
Yes, it's just a basic question. If we can use the percent theoretical amino acid to like the proteins for like the sampling, since we don't have much information on that. I guess could we like use the mass composition?
yes,
We don't have
yeah.
without putting on.
Did we identify it as 11S or?
We ever had that.
Okay.
You said it's like.
So from the molecular weight, do you remember what the molecular weight was? Was it when you did size it, did you do 5 to 3?
No swap thing.
Yeah, so one thing then we can discuss later, one thing you can look at the molecular weight and we try to determine is it the trimer, is it the hexamer, also that will pass from SES phase when you run it under reducing and non-reducing. So then we will know, is it visceral light, 7S, or is it legumin light? And then we can compare it to different 7S's and 11S's from different. Yeah, but running amino acid composition definitely we can use it very good. Yeah, very good. Yeah. Any other thoughts? Yeah,
Can you say that in the mind of? What is
ladder sequencing, and you can go back to this. Ladder, sorry, maybe I went through it very fast. Yeah, ladder sequencing is like, step by step. So if you have a peptide and you want to determine the composition of the peptide, you can break off one amino acid by either an enzyme or any chemical breakdown peptide and run it on, run through your LC-MS. Sorry, MALDI. Run it through your MALDI. And then do the cycle again. Yeah. So one sample at a time. No, you treat the sample outside. You treat the sample, you break off an amino acid, and then put it on the slide. And then you will read those different peptides that you read. Each one of them will be different by one amino acid. So if you look at the first one is 1229, and then the next one is 1344, the mass difference is as follows. And then you break the next one off, and then you see that the next one is 1473. The difference is glutamic acid. So that's the ladder. So one step at a time, one amino acid. Make sense?
Usually the peptides are starting on in the when pH decreases to isolate point. For example, in the protein, the peptides are soluble or
Most depending on the size of the peptide. Usually when you hydrolyze and you have peptides, they no longer have the same isoelectric point as the original protein. So they may or may not fall down, depending on their size and composition. They may or may, they're small in molecular weight. Less than
so
1
the
kilodalton.
Keldon is not the right way to.
Keldon?
Yes. Because it's a total nitrogen and we can
cannot understand, at least a native protein or is.
No, it will tell you something like this. Yeah, it won't differentiate as a peptide or protein. But you can take your different fractions, separate, and run them on the graph and see what you get and how the precipitate is different from what was in the soluble. So if you centrifuge, and then you have protein in the supplement and protein in the precipitate, take these two fractions separate, compare them, put on them on an SCS plate. Then you will know the composition of what's in supplement and what's in the precipitate. Yeah. Would be one thing to look at.
But it doesn't solve the theory of based on percentage, it just shows like how.
It might show you the extent of hydrolysis if you, so when you say degradation are not the correct term to use for protein. Degradation sometimes is hydrolysis, sometimes is denaturation. So if you're susceptible to breaking,
Yes, because for me it's a high meeting, so it's not a hydrolyte.
no, it will be denatured polymerize.
Yes.
It will be good after you centrifuge and separate to look at what you have in the soluble, what you have in the precipitate. That's like the first step to see what you separate. So, any other questions?
So
Yes.
on the centrifuge, the ones in the supernatant are the ones that are hydrolyzed or not necessarily?
It depends, well, soluble, they remain soluble. It depends on what you treated. If you treated with enzymes, you might wonder where your hydrolysate is. So you would look to see if all the hydrolysate are in supernatant or some hydrolysate also considered. If you're thermally treated, there's no hydrolysis, there is potentially polymerization. So it depends on the process that you do. All right. We'll continue the story. What? All right, so next we're going to talk about protein denaturation and impact of structural changes on functionality. So what I will be talking about next is what causes the protein to denature. And then I will talk about functional properties of the protein, and then we'll link structure to function. Okay, let's see what you remember. I know you all like this enthalpy entropy thing. Yeah, remember delta G equal delta H minus T delta F. Well, yes. Let's start somewhere. Well, none of them. It's a good guess. Huh? A. Okay, keep guessing. Well, I want to see you being a judge. I didn't say not A. I didn't say none of them. It's a good guess. This one. See? Correct. All right, so few weeks ago, we talked about very small bonds, it's few number of bonds, maybe 3 hydrogen bonds or something like that. We are decreasing enthalpy. Enthalpy is the contained energy, and entropy is a tax that is resulting of breaking bonds. So, and denaturation is additive. Like once you break two bonds, more will be broken very rapidly. So, and decrease in enthalpy, that means the decrease in the contained energy through the breakage of some bonds will cause a substantial increase in chaos, in entropy. Okay, so C. This one. Protein denaturation is induced by heat, or denaturation induced by heat, because protein can denature by acid, by alkaline, by different mechanisms. What's that? So what were you going to say? Did you say anything? You didn't say anything? Say something. A and C. Well, A and C, they're A and C are correct, but they're missing B. So all of them, we're gonna talk about, well, the salt one, it can, doesn't mean always, it depends on the type of salt and concentration. So, protein in solution will denature at lower temperature than dry protein, yeah? And I'll explain that and show you why. Sugars are cosmotropes. I don't know if you remember K-tropes, cosmotrope in different life. Cosmotrope are stabilizers. K-tropes, solutes, small molecular weight solutes, are destabilized. Some salts can be cosmotropes, some salts can be K-tropes. But sugars, small molecular weight sugars, are stabilizers. So in the presence of sugar, the denaturation temperature causes stabilization. In the presence of salt, depending on the type of salt, denaturation can be low, depending on type and concentration. Denaturation can be enhanced, then denaturation temperature can be low. Okay. I'll show you that I have images later. So when you have a cosmotrope, it binds loosely with the protein and enhances interaction with water. When you have K-tropes, it binds strongly with the protein and a lot of it, shielding the charge and preventing water interaction. So that's, but you will see it visually in a different slide. Okay. So this is our map again. We talked about intrinsic factors. Now, those intrinsic factors impact, amino acid composition and sequence, molecular configuration, molecular size, association, surface properties. This is the structure. Now, we go, depending on processing and environmental conditions, we go from native to denatured. Then we learned all the methods of assessing structural changes. Then we learn about these structural changes as we move from native to denatured, and then we'll see how that will impact functionality. So we're slowly building that puzzle together. So we don't usually eat raw food, with the exception of your vegetable salad and your fruit. Often we process ingredients and products and food products to make them safer, whether by inactivating microorganisms. Well, we have the pathogenic microorganism and we have the spoilage microorganism. So sometimes treatment is to get rid of pathogenic. Sometimes you want to get rid of even spoilage microorganisms. Inactivation of enzymes that might impact the color, the flavor of food, the texture. And then we cook to develop flavor and texture. So develop a desirable flavor, desirable texture, to make things more digestible, to get rid of some toxic components, inhibit some toxic components, saponins, for example. So we have reasons for processing of food. But if we think about the impact of processing on the protein itself, not just everything else, this is everything else. But if we think about, so improvement of nutritional value, that could be, for example, raw starch, we cannot digest, cooked starch, gelatinized starch, we can digest. So this can be applied to everything. But if we think about protein, what changes are desirable? Can you think of desirable changes when we talk? Or when we Huh? Marginally enhance ability. Huh? A good thing. You want to talk about good thing? We're coming to the bad thing. What are you decreasing? No, I'm decreases. What? Sometimes solubility decreases. Okay, yeah. But what is something that we do? Let us say thermal treatment that's actually good in terms of protein content. Huh?
The partial denaturation, for example.
Partial yeah.
Improve the functional.
Improve gelation, emulsification. Yeah. So partial denaturation or sometimes complete denaturation and formation of ordered polymers like in a gel. Okay. What else? Think of trypsin inhibitors. What are they? They are proteins. The cross.
Can you mention about the makeup?
Yeah. Sometimes it's good, sometimes it's not. In bread, you want the brown, so it's good. In a beverage, reducing sugar and protein is bad, so then you get brown. Okay, right? Partial denaturation enhances digestibility. Those plant proteins, they are globular, they are hard to digest. Enzymes have hard time going in and breaking the bond. So partial denaturation, unfolding allows the enzyme to digest. So partial denaturation is really good. So that's some of the desired. Oh, undesired is excessive denaturation and polymerization becomes insoluble. So forming of large aggregates. If you want to use a bed form of beverage, not good. If you want to even form a gel, it's not good if you start with excessively denatured and polymerized. So this insolubilization is not desired. Excessive polymerization actually makes it harder to digest. So now you denatured the protein, but now you form large blobs of it. The enzymes will have a hard time digesting. And inhibition of desirable enzymes. For example, when you want to make cheese, so you form your cheese from milk, obviously, and then there's aging. If you inhibit some proteases and other enzymes that are needed to develop the flavor during aging, that will be a problem. So that's why heating milk for cheese is done at different conditions than heating milk for other uses. So that they want to prevent inactivation of some desirable enzyme. That's an example. Maillard reaction, it's in the middle, like we said, sometimes it's desirable, sometimes it's not. Okay. So this is just to remind you, we're going to be using this delta G equation. And then this is the delta G when it's positive, then the protein is stable. When you break few bonds, the entropy will increase. And then that will give you a negative delta G, and that will cause spontaneous denaturation. This is just reminding you of what we talked about before about the formation of the peptide, has a lot of free energy, and then it bends and folds to contain the energy through bonding. But then you have limitations, steric hindrance due to the R group, basically. So this just to remind you of these concepts as we talk about denaturation. So the concept of free energy, containing energy, breaking bonds, forming bonds. So what I'm showing here is, again, we talked about the impact of hydrophobic groups in the formation of the protein structure. So what happens is, just as a reminder, the hydrophobic residues tends to, associate with each other, and the water is pulled to the outside. So these blue structure is a water structure around the protein in the most stable form. So when we have but we still have hydrophobicity on the surface, but when we get to the most stable form by containing the energy, and the water now forms like ice-like structure around the protein, and we get to the stable form in aqueous. So what this says is it's basically a different way of saying reaching a stable form. It's entropy driven, meaning entropy driven is the energy contained and released. Okay, that's entropy is when the energy is released. Contained and released, reduced and increased. At low temperature, we have a positive delta G, and denaturation is unfavorable. As you increase the temperature, and we know also it's moisture dependent, we'll talk about that. Then if we get to a negative delta G, denaturation becomes spontaneous. So when you heat, all proteins are prone to denaturation, but each is prone to denaturation at different temperature, and also it depends on the environment, the pH, the ionic strength, the concentration of the protein, and the amount of water. But at an X elevated temperature for an X protein, what happens is unfolding, and now the hydrophobic groups are exposed to water, and we break the stable water structure. So now entropic term dominates, so delta S goes up, delta G becomes negative, protein denaturation becomes spontaneous. So when entropy increases, that means when you break some bonds, you have this extra energy happening. That's the thermodynamics happening, thermokinetics. So that facilitates the unfolding by breaking more bonds. More chaos causes chaos. Now, this is something that will explain a lot of phenomena later on, but hydrogen bonding, electrostatic, and van der Waals are exothermic. So that means when they form, they release heat. So when there is heat, they get destabilized. Whereas hydrophobic interactions are the opposite. They are endothermic. So when you give heat, they are going to be stronger and more can form. More hydrophobic interactions can form. However, if you keep increasing the temperature, and then the unfolding happens, the water structure breaks. And when the water structure breaks, that will cause this denaturation and breaking of even hydrophobic bonds. Because when the protein unfolds, even hydrophobic bonds in the interior moiety of the protein will be starting to break so that the protein unfolds. So although increase in temperature can strengthen hydrophobic interaction, but at a certain point with water breaking, we can actually reduce hydrophobic interaction. Huh? The structure? Yeah, this kind of isolate structure. Which can cause more destabilization. Okay, so this is just illustration of how the transition happens. So you have native, you go through that transition when your entropy is increasing, you're breaking bonds, and then you will get an unfolding state. But after that, we don't just stay at unfolding. With more heat and more protein exposure to each other, we start forming polymerization. And sometimes you get to a soluble aggregate state, which is beneficial for some application, but excessive heat, longer time, more aggressive treatment, you get an insoluble aggregate state, which goes into precipitation, and that will not be for all functionality. So here's just lowest free state. We talked about it. That's the native state, most thermodynamically stable state. But that denaturation and native state are dependent on the environment. I said that. So it's not like protein exists in vacuum. Really, it is pH. What's the pH? What's the moisture content? What's the salt content? How much protein you have in the system? They play a role in going from native to unfolded to polymerized to aggregate to precipitate. And this is showing the transition from the native to denatured and then to an aggregated state. So when protein is denatured, we say here ill-defined, meaning we try to resemble it to random coil, but it's not always, all of it is in random coil. Sometimes we have a conversion of alpha helix to beta sheet, sometimes beta sheet to beta turn. So it's not really accurate to say all the nature proteins are in random coil. But in general, we illustrate it as a random coil structure. And sometimes denaturation is reversible, and sometimes it's irreversible. So that's why I wanted Kevin this. How am I going to use this?
That it will come back.
Uh-huh.
And then
So yeah, so take an elastic. Okay, think of the protein as an elastic. You apply stress, but for a short period of time, it comes back to where it was. That means you apply a few seconds of heat, or you change the pH and then brought it back quickly. That's why we don't want to keep it at the isoelectric point more than 2 hours. But if we stretch and go to sleep like that, come the next morning, it's not going to go back to where it was, because now we overstressed it. So either the temperature was high for a long period of time, or we put it at denaturing conditions for a long period of time. And sometimes, especially if the proteins are prone to forming disulfide linkages, we allowed it time to form these linkages, then this is normal. Okay, so it has to do with the stress, and also it has to do with the nature of the protein. So today we had a meeting. So one of the PPIC members, they asked me, can we make pea protein gel irreversible, like collagen? Collagen going into gelatin, the process, right? So you have collagen, you heat it, and then it forms this amorphous structure, gelatin, and then you cool it, it forms a gel, you heat it, reversible. Can we do that with people? He's laughing at me protein. Can we or can we not? I'm assuming you're correct. No, we cannot do that because they asked me why. I said it's physiologically impossible because collagen is stabilized by hydrogen bonding. So when you heat it, you're breaking hydrogen bonding. Remember, there are exothermics. So you break those hydrogen bonding, and then you cool down. You form them again, but not in the same way. That's how collagen converts to gel. They become solid gel, and then you heat, you're breaking those hydrogen bonds again. And then that's why it's reversible. But in pea protein, so you heat it, you denature it, and then what happens? Strong hydrophobic interactions take place. This is very hydrophobic protein, very different than meat protein collagen, and you have disulfide linkage. And once you form these strong hydrophobic interaction coupled with covalent linkages, no reversibility. And here we're just saying that the changes in structure is sometimes conformationally adaptable. So think about enzyme activity. So if you want to have optimal enzyme activity, you need a specific pH. Sometimes you need to add a specific ion, like calcium, for some enzymes to work. So by changing pH or ionic strength or temperature, you are adapting the structure to allow substrate enzyme binding. So that's why you're not denaturing, you're adapting the structure. Okay. So let me explain what you're looking at here. So on this axis, the x-axis is the denaturing, whether temperature, increasing temperature, or changing the pH in a certain direction, or adding a denaturant, like say urea or SES. And then the y-axis is what you're measuring. Sometimes you're measuring surface hydrophobicity. So it would increase. Sometimes you're measuring solubility. It would decrease. Okay, so the y-axis could be whatever you're measuring, an indicator of denaturation. Or enzyme activity, for example. So the reason this is very steep, down, up, like there is not like slowly changing, it just goes up or down. That's because denaturation process is cooperative process. Meaning, once you break few bonds, it's kind of a cascade action that you can't stop, like domino. Hit couple and then the whole thing will collapse. So it is a cooperative process, starts with breaking few bonds, and then all X breakthroughs. Okay. So how does amino acid composition affect thermoset? From what we learned earlier in this semester. Can you give an example where amino acid composition can result in higher denaturation temperature, lower denaturation temperature? Yeah.
I was thinking maybe of the amino acids in the protein are more like hydrophobic ones, and that will make it more stable and less higher denaturation temperature.
Yes, that's a good example. Higher degree of hydrophobicity. Very good. What else? Can you give me another example related to amino acid composition?
High sulfur containing.
High
Sulfur containing amino acids.
sulfide groups. Yes. you will form disulfide linkages, then you will have higher temperature of denaturation, more stable form. Very good. And it's right there. Is it on the slide? No, no. You guys got it. I was like, did it need it? Okay, good. Very good. Also, if the more ordered structure you have. So we talked about beta-lactoglobulin is very ordered. You have secondary structure, beta sheet, alpha helix. If we look at casein, they're very amphiphilic, hydrophobic. They form these calcium phosphate bridges. So they are not easily denatured. So they denature, I think, 140 degrees C when they start to be denatured. Yeah. So the structure, if you have a monomer versus a quaternary structure that is stabilized by more different bonds. Okay. Here is also a table. For example, I remember when I told you convert some bad tables and figures and get extra credit. Maybe all of you will start doing that after the lecture. Now you don't have any incentive to help me out. This is an example of somebody helping out with a table, an old table. You know, I have plenty of those throughout. Okay, we'll wait. Here is an illustration. So soy glycinin and P legumin, they're both 11S. So they're both hexamer, quaternary structure, globulin proteins, but the soy glycine is very breeding over the years made it very consistent. P is still very valuable. So you see, it's always denatures at 92 degrees around there. P legumin, it can be even 85, sometimes even lower, 82, 83. It can go up to 95. What causes this difference? Those of you that work in the lab, why soy denatures usually at higher temperature, the 11S than the 11S in P? There's a unique characteristic. Soy has more sulfide groups. So glycinin in soy, usually it has more sulfide groups. But P, depending on the cultivar, it varies. Some cultivars has enough cysteine to stabilize it, some don't. Beta-conglycinin denatures, which is 7S, it's a trimer, denatures at lower temperature because there's no sulfide disulfide linkages. So you see that difference in denaturation temperature. Same with vicilin, it's also a 7S, a trimer like beta-conglycinin. It's very similar, but again with P, we see that range because of a lot of variation in different breeding lines. And beta-lactoglobulin, 78 is the higher end, usually 73, 75. But yes, if we see the difference, alpha-lactalbumin is 62. It has more alpha helices. Beta-lactoglobulin have more beta sheet. So the beta sheet is more thermally stable. Okay, so this is linking composition and structure.
It's not related to the profile. It's related to the first structure.
It's related to their secondary structure, yes. More to their secondary structure. Because they do have disulfide linkage. But the ordered secondary structure is more prone to the denaturation, even though you have disulfide.
Among of the side hypoxia group in the alpha-lactoglobulin less than the
Yeah, but it has a lot. No, alpha-lactalbumin has more disulfide linkages than alpha. Yeah, I think it's like stay. I have to remember. It's in one of my slides later on. It has more, but it has alpha helix. So denaturation can happen at different levels, right? So yeah. This is linking water to protein denaturation. The higher the water, the lower is the denaturation temperature. So, and this is the figure, what is illustrated here. This is in Kelvin for some reason. And then this is water content. And you see that with the higher water content, you get a lower denaturation temperature, and then you get a plateau. It doesn't change after that. But the drier the protein, the higher the denaturation temperature and the higher is the enthalpy. So in our lab, for example, we always measure protein at 1 moisture content so that we can compare them. So we do 20% protein usually. So that all of the denaturation temperature and enthalpy is corrected based on protein content under the same water condition. So that we're comparing apples to apples. So in dry state, the protein is in static mode. So it's like not moving, not impacted by any moving water phase. So, but when we hydrate, water goes and penetrates the structure of the protein and starts forming those structures around the protein and penetrates into cavities. What happens? Starts swelling. So then what? Water starts interacting with protein. We're breaking hydrogen bonding because water is interfering in the bonding state. And you enhance the thermodynamics and the movement in the presence of water. So yeah. So if we want to explain denaturation, it's simple unfolding and changing the ordered structure or the most stable ordered structure of a native protein. When a globular protein is denatured, it resembles a random coil, but that doesn't mean you lost completely all secondary structure. So it's not like if you run it on FTIR, all you read is random coil. No, it resembles like a jumbled mumbled structure, but it's not. Not all random coil, you still have some data sheet, you even have some alpha helixes, but the protein opens up, unfolds. And then there is a gradual impact on the protein. So you have loss of quaternary structure, we call it dissociating. It's not a structural denaturation. So when the quaternary structure is disrupted, we call it dissociation. And sometimes we can reassociate. If we change the conditions, we can get the association again. But then there is unfolding and denaturation at the tertiary level and at the secondary. If you break bonds by hydrolysis, there is denaturation at the primary level. And like I said, sometimes it's reversible, irreversible, depending on the stress. Remember the coil, the elastic. So short-term partial unfolding, some of the native protein configuration has been preserved and can go back to the native state. Protein concentration in the solution plays a role. Why? Because it impacts the formation of polymers. So if I have 5% protein versus 15% protein, when I heat, the 15% protein have more molecules closer to each other, so more prone to form these polymers. So protein concentration is important in formation of aggregates. Okay? That's why it's very wrong when you review your paper, some of you did not select papers yet. If you review and then you see people measuring protein solubility at 1 milligram per mil. What's 1 milligram per mil in percentage? Is it like 0.1%, 0.1%. That means nothing. That is, oh, it's protein is very soluble, oh yeah? But we don't prepare protein beverages at 0.1%. Protein beverages, to claim high protein, they must be at least 4.2% protein. So when you review your papers, be very critical in what does it mean they enhance solubility? Yeah, well, 1 milligram per ml means nothing. Because protein concentration really plays an important role in whether or not the limit aggregates and precipitate up. Okay, so I will stop here. Now we're gonna talk about different than thermal denaturation. Okay, thank you guys. I hope you're not too tired. Who's as excited as me when we talk about protein? Nobody.
But beta-lactam has higher sulfate than alpha. It has a 5-16 and alpha-lactam have a 4-16.
Four double bonds, so it has 8 cysteine, alpha lactalbumin. And beta lactoglobulin has 2. I think this is what I remember. Come, I have the lecture here. Come. I hope.
Today I saw a picture that the reason for the establishment of alpha-lactam was exactly.
I mean,